Welcome, students. So this video will be talking about putting some real-world implications on some of our kinetic stuff. So far we've just kind of been looking at data. Now we're going to try to look at this in a molecular type situation. So we'll go ahead and get started. Okay. So as I said, we just had a bunch of math. A bunch of math that talks about rate laws and directly relating concentration with time based on the chemical reaction rate. But we want to look at this on a molecular level of what does this all mean? Well, this is going to be similar to our gas chapter when we talked about the kinetic molecular theory of gases. Well, gases bounce around, that they have so much energy based on their temperature, and all reactions are collisions, essentially. So we're going to go under that same collision-based model when it comes to understanding chemical reactions, that these molecules are bouncing around, and some have certain energies, and when they collide, they will react. So our premises are: 1, all molecules, whether they be gas, liquid, or solid, are moving at random. Obviously, there are some constraints over liquids and solids on how they can move. The energy is transferred via collisions. So when they collide, they're essentially elastic collisions. And it's inelastic, where they kind of just transfer energy. Okay, then there's a broad distribution of energy based on the temperature, that some molecules are moving fast, some molecules are moving slow. But the average energy is based on the temperature. Now, the new premise basically is that all reactions are a result of collisions that depend on 2 things. 1, the orientation of the molecule, like what way it's facing when it collides, and the energy of the collision. So, if you run into the wall, if you run into it face first, it might hurt a little bit more than if you turn and skid and slam into it from your side. If you put your foot up and kick the wall to stop yourself, it's going to hurt less than if you slam your head into the wall. So, depending on how you're oriented, depends on how much damage the wall does to you. Same way, molecules can ricochet into other molecules if it hits in such a way. It doesn't matter how hard it hits, if you can't form a new bond, breaking bonds doesn't occur. Now, of course, if you just bump into something with very low energy, you're not going to do any damage. There's no reaction. But if you hit on hard enough, bonds will break. It will shake atoms free. So it needs those 2 things. So we're going to look at a reaction diagram. These reaction diagrams will be useful all throughout general chemistry and organic chemistry to help just picture what is going on. That these are very informal, that there's the scale is generally just, we have an energy scale on the y-axis and a reaction scale on the x-axis. Not really even much of a scale on the x-axis, it's just showing reactants and products. So the reactants have a certain amount of energy and the products have a certain amount of energy, and that's going to relate where these 2 valleys are with respect to each other. Now, typically there is some sort of hill between those 2 valleys, and that hill is related to the energy it takes to make the reaction go. So this reaction diagram will contain the reactants. The product usually will show some sort of activation energy, which is E sub A, energy of activation. It will show some sort of enthalpy value, which is the heat that is either produced or consumed. And that is the difference between the reactants and products. and we'll have some way of looking at the transition state, which is the state in between product and reactant. So looking at this reaction, we have NO reacts with O3 to form an NO2 and one O2. So essentially the N must collide with the O in such a way that it breaks the bond between the O3 and comes onto the N. Now, if the O hits another O, it's not likely to react, but we need the N to hit that O in the ozone. But so the transition state is the state that occurs at the peak energy state where the bonds are neither fully broken or fully formed. So this is a transitioning between the reactant and product. It could go either way. It doesn't have to go to product from that transition state. But transition state is usually something that is mostly theoretical because you cannot capture a transition state. But it helps us kind of think about what must be going on. Now, the enthalpy, of course, is the difference in the energy in the products and the reactants. Regardless of the number of steps of a reaction, we have right here a one-step reaction being shown. But if there's 3 steps or 4 steps, we only care about the first and last step. We only care about the starting material and the final products. That's because, remember, enthalpy is a state function. So if I have to spend 5 kilojoules and another 3 kilojoules and another 2 kilojoules, so I've spent a total of 9 kilojoules. If I get back 10, well, I get 1 kilojoule back. It's a net exothermic of 1 kilojoule. So I only care about where I end up regards to the final product and the reactant. Now, the activation energy is the difference between the reactants and that transition state. So what hill do I have to climb before I can roll back down to the other side? Now, this activation energy is going to be directly related to the rate constant K. Note, if you're on the product side and trying to go back to reactants, which it's possible to do, in this particular situation, the activation energy would be higher because it's not from R to this, it's from the P all the way up, and so it's a higher hill to climb. So our activation energy. So recalling our bond enthalpy and the energy it takes to break bonds. Even if the reaction is net exothermic, if the bond doesn't break, no reaction can occur. So no energy is produced. So we always have to overcome the activation energy before a reaction can occur, even if it normally wants to occur. So the molecules need to collide with a certain minimum energy needed for the reaction to occur, and that's the activation energy. Each activation energy will vary depending on the reaction that's been happening. But if you remember the distribution diagram of molecules with various kinetic energies based on their temperatures, you can see here, like, hypothetically, the atoms at 0 degrees has very few atoms that have enough energy to react, so it's going to react very slowly. At 20 degrees, it starts to shift over, and we have more molecules at higher energies, and we have more molecules that are above the reactive diagram. At 50 degrees, the molecules are moving even faster still, and maybe about 50% of the molecules, when they collide, will have enough energy to react. So more temperature means more likely of overcoming the activation energy, means faster reaction. Now the orientation factor is a little bit harder to calculate and a little bit harder to understand. But molecular orientation is key to how the collisions occur. That if I have, like, for example, as shown here, if NO collides with O3 and the O hits the O, they're probably not going to make another bond, and so we don't have a reaction. But if we have a N bumps into the O, there's a chance that the O will be lost and you will form the new bond. So now the orientation factor will be considered in the equation by using a constant A. The constant A for a given reaction takes into account all the possible collision angles and the combinations, and says there's a specific number of possible collisions that could make this reaction occur, assuming they have enough energy. And that factors that in. However, this is going to be less important value than our activation energy. So that gets us finally to our mathematical equation that we need to consider. The reaction rate will depend on both possible orientations A and the activation energy E sub A. However, the largest dependence is on E sub A. So a Swedish physicist by the name of Svante Arrhenius, who we'll look at later when we talk about acids and bases, wrote in a nice equation that helps understand this. He was the first to propose a relationship between temperature, activation energy, and reaction rate. And so our equation is K, so our rate constant K equals the orientation factor A times the exponential, so that's the special constant E, the inverse natural log E, raised to the power of negative activation energy over RT. So it takes into account, the rate constant K takes into account the orientation factor and the activation energy, which is dependent on temperature. So as long as the reaction is done at the right temperature, K is essentially constant. Now activation energy is usually in kilojoules per mole, so R is in joules per mole, and we have to convert one of those. And A takes into account and gets the units right. However, that is not always a very convenient equation. So the more convenient version is to compare these two, and we're going to take a natural log of our equation. Natural log of our equation turns the K into ln of K, and it turns our exponential into negative E sub A over R, which is a constant, times 1 over T plus natural log of A. So right there, that looks like a linear equation. In fact, using just 2 points on a graph, we can determine the activation energy and the orientation frequency. But essentially, this should look surprisingly similar to our vapor pressure equation, which is why I had us study that a chapter or so ago, because this takes another chance to rear its ugly head. So, that in mind, you can do this. Just remember, temperature needs to be in Kelvin. So looking at these two problems, we have, what would the activation energy be? Reaction where the rate constant, K, so if it's 5.4 times 10 to the negative fourth, at the T of 25, and had a K sub 2 at 11.2 times 10 to the 24, so 1.12 times 10 to the negative third, essentially. T2 at 35. And then the last question is, then what would that rate constant be? Well, what's K3 if T3 is 50? So with that in mind, this is essentially our video. Okay, looking at this. So I'm going to do some of this on Excel, but I just wanted to show you set this up. So in this case, we have two values. We need to turn this into Kelvin, 298, and Kelvin is going to be 308. As long as we've associated which one is which, we can do this. You just got to write the correct equation, plug them in. So how would I go about solving this? I'm going to set that up. Whatever K1 is and whatever T1 is, I'm going to say, okay, this guy is 5.4 10 to the negative fourth over 1.12 times 10 to the negative third, which is approximately, one way to look at it is 5.4 over 11.2. The 10 to the negative fourths cancel out. We take the natural log of that. Figure out what is this? What is this? Let's solve that first, because that's easy to do. ln of 5.4 over 11.2. That's negative 0.7295. I'll give it one more decimal just to make sure. That's equal to E sub A over R, 1 over T2, so 1 over 308, minus 1 over 298. So 1 over 308 minus 1 over 298 is a really small number. .314, and I'm going to divide that by 8, so negative 0.30, 108951. Divide that by 8.314. That goes even further, so EA negative 13105. So if I take that number and I divide by this number, I will get our activation energy. So I divide that by, so we have activation energy in joules as being 55,667 joules per mole. So that's one way to do this. I'm going to go to Excel and we'll do it again. So with that in mind, let's look at Excel. So we want to know E sub A. We want to know, so I'm going to just label things K1, K2, K3. K1 is 5.4 E negative 4. 11.2 E negative 4. We don't know K3 yet. Let's say T1, T2, T3. We have 25, 35, 50. This plus 273. Now, the brilliant part is, so you notice how in this formula that we have, it's relating to the box, not the number, the box. So it says E2 is equal to E2 plus 273.15. So if I change this number, this will automatically change. So if I say 26, I say 59 or 58, it changes because it's referring to the box and not the number. Now here's a neat thing. So you notice I scroll over here. This is a plus sign, it changes here. If I scroll down right to the pip corner here, it changes from a fat plus to a skinny plus. This allows us, the skinny plus allows us to drag formulas. Drag formulas across and down. So I want the formula to read whatever's in row 2. We're going to add 273.15 to it. So I'm going to drag that across. And what do you know? We get 308.15, 323.15. I've calculated my T. I've calculated my T's at all temperatures. Okay, with that in mind, I got my K's, I got my T's. If I want to, I can do many different things from here. I can set up the formulas, or I could graph this. So with that in mind, I'm going to graph this. My graph needs to be natural log of K over 1 over T. So I'm going to say natural log of K1, natural log of K, and 1 over T. So to do the natural log of K, I have to equals ln, parentheses, and I'm going to grab that number. Say, what's that natural log? I can do the second one. ln, what's that number? One over T, it just equals 1 divided by my temperature. Equals 1 divided by my temperature. I have 2 points, and you can always draw a straight line out of 2 points. So I'm going to highlight these, and I'm going to insert a graph. So I'm going to always insert a scatter plot. Okay, this did it funny, so I'm going to try again. Delete that. See if I can graph it like this. So I'm going to insert a scatter plot. Yeah, there we go. The important thing, nope. Yeah, the important thing is, okay, now I graphed it funny. Now we're going to have to change it again. So I'm going to select my data. So in this case, I'm going to row with columns. Yes, I want to switch rows with columns. Now this should plot it just fine. The important thing, though, is I want this as my X and the ln of K as my Y, and it's done that wrong. So I'm going to just select the data, and we'll have to do it fresh. So in the chart, I'm going to click my series, and I'm going to edit. And it says X values. Right here, we're going to go X values. I'm going to click on this little arrow button and select what values I want as my X. I'm going to just grab and drag those 2 boxes. It'll label them how it needs to label them. You don't have to learn how to label that just yet. But for my Y values, I'm going to select these 2 boxes. And that will plot this. So now we're plotted. And mine, I can hit OK. Now that it's correctly plotted, we'll have a nice straight line. However, I'm going to want a trend line out of this. If I add a trend line, I can do a linear one, and I want to show the equation. Show the equation. Now the equation of this trend line will give me all I need. Remember the equation, I'm going to write this on the thing, even though it's stupid. So it's like ln K equals negative EA over R times 1 over T plus ln of A. Well, so that means our slope, our M is equal to, M is negative 6702.4, which is negative EA over R. EA over constant. Oh, I don't want it equal. That's the problem. That's the problem. It's confused because it wants to try to write an equation. Okay. So it's EA over R. Let's see if it'll do that. So it's negative EA over R. And our y-intercept, B, is 14.956. And this is ln of A. So with that in mind, I should be able to find what is my activation energy. So I'm going to take this value and I'm going to multiply by negative R, negative 8.314. And what do you know? I got an activation energy of 55723.75. So it's 55,000. The one I solved previously was 55,667. It's a little off, mainly because there was a decent amount of, well, there was some rounding involved. So, and plus I did 298.15. If I change those values, let's see if how much it changes this. 298 and 308. So this becomes negative 6695. 6695. And what do you know? Because I used 298.15, it changed my values ever so slightly. Ever so slightly. Because I didn't use the proper one. Now, to get the A factor, I would have to type E, what equals exponential of this value here. If I type the exponential, there's my A factor. It's a really big number. That is okay. That is okay. We don't usually look at our A factor. Now, with that in mind, we know our T. So we know our T. So because we've already plugged this, we can solve this real quick. So equals 1 divided by my T. Well, we can figure out, so our slope, our lnk must equal this times this plus this. So there's our lnk. That's good. Should fit along the linear pattern. So this equals, well then we just have to type exponential of our K3, and we have our answer. So let's put this into scientific so we can compare. So scientific, 307 times 10 to the negative third. 307 times 10 to the negative third. It's moving a lot faster, almost 33 times faster than in K2 when I have increased the temperature from 35 to 55. Now, if I added, of course, if I added, edit, grab all these, it should fit the data. Numbers are the same, or slightly changed, slightly a little bit smaller. for the most part, things stay more or less the same. So that is an alternative method of doing this rather than pencil and paper. Notice how one thing I did try to do is I tried to label things. As long as I'm labeling things, I know what these numbers actually refer to. On paper, you can label your units. On Excel, it's a little bit harder, but it is absolutely possible. What I'm trying to show you is that, hey, look, if you can use Excel, it is great. It is amazing. It's fantabulous. But if you can't use Excel, I mean, I want to teach you at some point, but that can wait. But so 669 and 307. What did I get on my Excel? I got 307 exactly. So my method worked rather easily. And even with this slight error in my activation energy, then we still got the same K constant. Now, we'll go ahead and finish off this chapter. I mean, I don't really know. I'll just keep going. Yeah, we'll keep going. So, actually, no, I'm going to stop. My bad. So, that's where we'll stop for today. And we'll finish off this chapter in the next video.